Continue on physical chemistry, chapter 17. We're in section 3 now. In section 3, we're going to be performing integration of rate laws. Now, one type of reaction is a zero-order reaction. This actually is very uncommon in chemistry. An example might be enzyme catalysis. So here's an example. We have R is equal to K prime times the concentration of substance A to the 0th power. Therefore, it's just R is equal to K. So this is a zero-order reaction. So this is how a reaction might be. So we have A amount of substance A going to one or more products. So here's a two-dimensional graph showing the rate of the reaction versus the concentration. So you'll notice it's flat. No matter what the concentration of A is, the rate is constant. So in this case, we'll just say R is equal to K prime. So here's the formula. Minus 1 over A times the derivative of the concentration of A with respect to time is equal to K prime and is equal to R. Remember, lowercase t is time. So we're going to solve for the differential of the concentration of A. So we get minus the differential of the concentration of A is equal to lowercase a times K prime times the differential of time. Now we can integrate that. So we're going to get A times, we're going to say A times K prime is equal to K. Since A and K prime, they're both constants. So we get minus the differential of the concentration of A is equal to K times the differential of time. So we have the integral of minus the differential of A is equal to the integral of K with respect to time. So we get remember the integral from A naught to A. So A naught would be like the initial concentration of A to the current concentration of A. Of minus differential of A is just the integral from time 0 to whatever current time we're at of K dt. So the left side gives us minus the concentration of A evaluated from A naught to A. So the initial concentration of A to the current concentration of A. And that's equal to the constant K times time evaluated from time equals 0 to the current time. So substituting that in, we get minus the concentration of A plus the initial concentration of A is equal to K times the time minus 0, because we're saying time minus initial time is equal to 0 time. So simplifying that out, we just get the concentration of A, the initial concentration of A minus the concentration of A is equal to K times T. So this is the integrated rate law for a zero-order reaction. And then we can solve for just the concentration of A, and that's equal to minus K times time plus the initial concentration of A. So here's a graph of how it looks like. We have the initial concentration of A minus A versus time. So over time, it goes up. The slope of this line is equal to K. But this is only true for a zero-order reaction, remember. So this is, here we have the concentration of A versus time. Remember, A is the reactant. So obviously, as time goes by, the concentration of the reactant will go down. And in this case, the slope will be minus K. And this, again, is only for a zero-order reaction. So an example might be a reaction that happens on the surface of a solid catalyst. Because in that case, the catalyst, you've only got so much surface area for the reaction to happen. Now let's talk about first-order reactions. Now these are very important, very common. And this you should memorize for the test. Now, an example of this might be radioactive decay, nuclear decay. And that's always first order. It's not really chemistry, but it's sort of a cousin of chemistry. Nuclear chemistry. So anyway, we have A amount of substance A going to one or more products. So the R, remember, is the rate, and that's going to be minus 1 over A times the derivative of the concentration of A with respect to time, lowercase t is time, and that's equal to K prime times the concentration of A. So we have the derivative of the concentration of A with respect to time is equal to minus K times the concentration of A, where we say K is equal to A times K prime. Now we're going to separate the variables. So we get A and T, A on one side, T on the other. So we have the derivative of the concentration of A divided by A is concentration of A, obviously, is equal to minus K differential of time. Now we can integrate that because we separated the variables. So you have the integral from the initial concentration of A to the current concentration of A of 1 over the concentration of A with respect to the concentration of A. And that's equal to minus K times the integral from 0 to T dt. So that gives us the natural log of concentration of A evaluated from the initial concentration of A to the current concentration of A. And that's equal to minus KT evaluated from 0 to T. So that gives us the natural log of A minus the natural log of the initial concentration of A equals minus KT. Or we can get the natural log of the concentration of A is equal to minus KT plus the natural log of the initial concentration of A. So then we can write it, the natural log of the initial concentration, or the concentration of A divided by the initial concentration of A is equal to minus KT. All we're doing is algebra to move stuff around here. So then we have the initial the concentration of A is equal to the initial concentration of A times E to the minus KT. See what we do? We took E to both sides here and just solved for the concentration of A. So we have a graph here of the natural log of the concentration of A versus time. Notice this is a slope going down. The slope here is minus K. It's only true for the first order. So the y-intercept put over here, that'll be the natural log of the initial concentration of A. Then we also here just have the concentration of A versus time. That's more of a curve. You still start out at the initial concentration of A, obviously. So this is a good graph if you're finding half-life. Remember, each half-life is going to be the same width on this time of graph. So this curve, it doesn't go all the way to 0. It's going asymptotically to 0 as time approaches infinity. So each distance for time 1/2 or half-life is the same amount of time for a first order reaction only. So here's another graph. This is natural log of A naught, so the initial concentration of A divided by A versus time. This comes out a nice straight line with a slope of K. So let's say that we want to find the half-life. So that's when T is equal to T 1/2. This is the symbol for a half-life. So that means the concentration of A is going to be equal to the initial concentration of A divided by 2. So we could say that for finding half-life, the initial concentration of A is equal to 2 times the concentration of A. So the concentration of A, remember, this is what's left in the system, not how much has been used up by the system. Because we're talking about the reactants. It's a reactant. This is what you started with. So the natural log of the concentration of A divided by 2 times the concentration of A is equal to minus K times time at 1/2, the half-life. So obviously those concentration of A's over here, they cancel out, and you just do algebra to solve. You get natural log of 1/2 is equal to minus K T 1/2. Approximating this irrational number as a decimal, you get minus 0.693 is equal to minus K T 1/2. So you get T 1/2 is equal to 0.693 divided by K. It's only for first order reactions. And remember this equal sign, it's really approximate because we rounded a irrational number to a finite decimal. So remember, of course, if you're taking a constant divided by a constant, you're going to get another constant. Now remember, you shouldn't apply this to a pseudo first order reaction though. So here's a couple of formulas. Here's CO NH2, 2, that's urea, which is a solid. And here's CO CH3, 2, that's acetone, that's a liquid. So urea and acetone, they're the same size and shape, but urea has hydrogen bonding, acetone does not. Okay, now let's talk about second order reactions. Now these are more common than first order reactions. Now there are a couple types we're going to talk about. The first, type 1, is we're going to go from A amount of A to products. And the second one we're going to talk about is we're going to have two different reactants, A and B, going to one or more products. So here we go for type 1 first. So the rate is going to be equal to K prime times the concentration of A squared. Remember, because it's second order. So we get minus 1 over A times the derivative of the concentration of A with respect to time is equal to K prime times the concentration of A squared. And we're going to say A times K prime is going to be equal to K. Now we have the derivative of the concentration of A divided by concentration of A squared is equal to minus K times the differential of T. Now that we got separate variables, we can integrate. So we have the integral of 1 over A squared with respect to the concentration of A is equal to the integral of minus K dt. So we get the integral from the initial concentration of A to the concentration of A of 1 over the concentration of A squared with respect to the concentration of A is equal to minus K times the integral from 0 to T with respect to time. Lowercase t is time, remember. So we have minus 1 over the concentration of A evaluated from the initial concentration of A to A is equal to minus KT evaluated from 0 to T. So we get minus 1 over A plus 1 over the initial concentration of A is equal to minus KT. So we can flip around the minus signs and just say 1 over the concentration of A minus 1 over the initial concentration of A is equal to KT for a second order reaction, remember. So here's a graph of 1 over the concentration of A versus time. Notice it's a straight line, it's linear for a second order reaction, and the slope here is K. So we have 1 over the concentration of A is equal to KT plus 1 over the initial concentration of A. So that's a line of just y equals mx plus b format. So we get T1 half is equal to 1 over A naught K. So your half-life is dependent on the initial concentration. With a first order reaction, remember, each half-life was the same. So here's a graph of the concentration of A divided by the initial concentration of A with half-lives. Each half-life is going to be a different amount of time because it depends on where you're starting out. Now the other type of second order reaction, the type 2, is where you start out with two different reactants. So we're going to have A plus B and then the constant K prime going to one or more products. So for now we're just going to say that lowercase a and b are equal to 1. So for that, the rate constant is going to be equal to K times the concentration of A times the concentration of B. So we have the derivative of the concentration of A with respect to time is equal to minus K times the concentration of A times the concentration of B. We need to separate variables. So we have the derivative of the concentration of A. I'll put it this way. Differential of concentration of A divided by the concentration of A divided by the concentration of B is equal to minus KT. Now remember, this B here is a variable, right? We can't integrate it like this. But we do know there's a relationship between A and B, right? So let's say this. The concentration of A, we'll say, is A naught minus X. So this X is going to be the change in the concentration of A. And then concentration of B, that's also going to be the initial concentration of B minus X. So we'll say that in differential form, the differential of the concentration of A is going to be 0 minus dx, and therefore the differential of A is going to be equal minus dx. So we're going to have the integral from x equals 0 to x of dx over A naught minus x and B naught minus x. And that's going to be equal to the integral from t equals 0 to t of k dt. So we're going to have to integrate using the method of partial fractions. So we're going to end up with 1 over the initial concentration of A minus x times the initial concentration of B minus x. That's going to be equal to 1 over A naught minus B naught times this whole quantity, 1 over the initial concentration of B minus x minus 1 over the initial concentration of A minus x. So for the left-hand side of this equation, here's how you evaluate it. You get 1 over A naught minus B naught, or the initial concentration of A minus the initial concentration of B, times this whole quantity, the integral from x equals 0 of basically 1 over B, initial concentration of B minus x with respect to x, minus the integral from 0 to x of 1 over the initial concentration of A minus x with respect to x. So that gives us 1 over the initial concentration A minus the initial concentration of B times this whole quantity here, minus the natural log of the initial concentration of B minus x evaluated from 0 to x, plus the natural log of the initial concentration of A minus x evaluated from 0 to x. Now we get 1 over the initial concentration of A minus the initial concentration of B times the natural log of the initial concentration of B minus x. This is actually initial concentration of B, or no, the concentration of B, remember. And then plus the natural log of the initial concentration of B, plus the natural log of the initial concentration of A minus x, which is the same as the concentration of A, minus the natural log of the initial concentration of A. So we can simplify and write that's equal to 1 over the initial concentration of A minus the initial concentration of B times this whole quantity here in parentheses minus the natural log of the concentration of B plus natural log of the initial concentration of B plus the natural log of the concentration of A minus the natural log of the initial concentration of A. Now we get 1 over the initial concentration of A minus the initial concentration of B times the natural log of the initial concentration of B times the concentration of A divided by the concentration of B times the initial concentration of A. And that's equal to KT. Now, for this, for a second order reaction like this, the half-life, it only makes sense if A equals B equals 1. So if we have T1 half of B naught over 2 and A naught over 2 is equal to what? Well, it doesn't make sense unless A equals B equals 1. So if we have coefficients, we get A amount of A plus B amount of B going to products, one or more products. So we get 1 over the A times the initial concentration of B minus B times the initial concentration of A times the natural log of the concentration of B times the initial concentration of A divided by the initial concentration of B times the concentration of A, and that's equal to KT. So here's a graph. Natural log of concentration of B times the initial concentration of A divided by the initial concentration of B times the concentration of A, all that against time, and still you graph it, you get a straight line if you have a second order reaction like we've been talking about. Then the slope here is going to be equal to K times A times the initial concentration of B times B times the initial concentration of A. And in this case, A and B are the same as nu1 and nu2. Okay, now let's say we have a third order reaction. Third order reaction, let's say we're going to have A amount of A going to one or more products. Then the rate is going to be equal to K times the concentration of A to the third power. Then we have the derivative of the concentration of A with respect to time is equal to minus, where'd I go? Equal to minus K times the concentration of A cubed. So we get 1 over the concentration of A squared minus 1 over the initial concentration of A squared. That's equal to 2KT. That's the integrated rate law. Now you can do any order reaction of the same type now. Let's say 10, 99, whatever n is. N is the exponent. So we're going to have substance A going to one or more products. Then our rate law will be R equals K times concentration of A to whatever n power. This formula won't work though if n is equal to 1. Anything else and it will work. So you have the derivative of the concentration of A with respect to time is equal to minus K times the times the concentration of A to the n power. So we're going to separate the variables. So we'll have the derivative of the concentration of A, hold on. We're going to have 1 over, we're going to have the differential of the concentration of A divided by the concentration of A to the n power, and that's equal to minus kT. Then we can integrate that. So we'll get the integral from the initial concentration of A to the concentration of A of 1 over the concentration of A to the n power with respect to A, concentration of A, and that's equal to minus K times the integral from 0 to T dt. So we get the integral from the initial concentration of A to the concentration of the concentration of A to the minus n power with respect to the concentration of A, and that's equal to minus K times the integral from 0 to T with respect to T. So that's going to give us 1 over minus n plus 1 times this whole quantity here, concentration of A to the minus n plus 1 minus the initial concentration of A to the minus n plus 1, and that's equal to minus kT. So we're going to multiply everything now by 1 minus n. So we're going to get the concentration of A to the 1 minus n is equal to the initial concentration of A to the 1 minus n, and that's going to be equal to n minus 1 times kT. Now we're going to divide by the initial concentration of A to the 1 minus A power. So we're going to get the initial concentration of A to the 1 minus n power divided by the initial concentration of A to the 1 minus n power minus 1, and that's going to be equal to n minus 1 times kT divided by the initial concentration of A to the 1 minus n. And remember, this formula won't work if n is equal to 1. So then we get the concentration of A divided by the initial concentration of A to the 1 minus n power, and that's equal to the initial concentration of A to the 1 minus n power times n minus 1 times k times t plus 1. And again, it won't work if n is equal to 1. Now that's good for any order, even fractions, as long as n is not equal to 1. So we can use that to find a half-life too. So we can say t, the half-life, is equal to 2 to the n minus 1 divided by n minus 1 times the initial concentration of A to the n minus 1 times k. And again, n is not equal to 1, and k is equal to A times k prime. Like for n is equal to 2, we can confirm what we already found before. T1 half is equal to 2 minus 1 over A naught times k, and that just simplifies the 2. How'd that happen? 1 over the initial concentration of A times k. Oh, 2 minus 1 is 1. Duh. So that confirms what we already did.